Daniela, and today I will be talking about quantum statistics and more precisely Bose-Einstein condensation. So, Bose-Einstein condensation is defined as the abrupt accumulation of atoms in the ground state at temperatures below a certain temperature called the condensation temperature. Something interesting is that this phenomenon happens only for bosons. So, what are bosons? A boson is a particle that has integer spin. The spin of the particle can be written as n, which is just an integer. In this case, h is Planck's constant and divided by 2 pi. When h is divided by 2 pi, we can abbreviate it as h bar. Bosons are particles that carry energy, and some examples of bosons are the photon, the gluon, the W and Z bosons. So what exactly is special about bosons? Well, bosons do not follow Pauli's exclusion principle. Recall that Pauli's exclusion principle states that two or more identical fermions, which are neutrinos, leptons, quarks, electrons, cannot occupy the same state. Instead, bosons follow what is called Bose-Einstein statistics. So, how was Bose-Einstein condensation discovered? Well, photon statistics, which is the quantum statistical property of a massless Bose particle, was first studied in 1924 by Bose. This work was later generalized by Einstein to an ideal gas of identical atoms. He predicted that at low temperatures, this ideal gas was a system of non-interacting or locked massive Bose particles. This was the basic idea of Bose-Einstein condensation. Atoms existing in the same quantum state, which corresponded at the lowest or ground state of the system. So these atoms are called a condensate. So considering the temperature of absolute zero, at this temperature all motion of the atoms stops and the atoms would be at the lowest energy state. Now, recalling that bosons do not follow the Pauli exclusion principle, all the bosons would be able to stay in the lowest energy state at the same time, so the ground state. So how do we describe Bose-Einstein condensation mathematically? Well, for this we use quantum statistics. So before we can describe Bose-Einstein condensation, I need to explain a few concepts of quantum statistics. So I will start with the Gibbs factor. So this derivation is very similar to the derivation of the Boltzmann factor for an isolated system, where all the accessible microstates are equally probable, and the isolated system here is the atom and the reservoir together. So we write the probability ratios of an atom being in state 2 versus state 1, just like we did in chapter 6. Recall that the probability is multiplicity over number of microstates. So then we can express the probability ratios as shown in the top equation here. And then we notice here that the exponent has a change in entropy, which we can then use the thermodynamic identity to further explain. So remember that whatever is gained by the reservoir must be lost by the system. So in this case, if we have the energy, volume, and number of particles of the reservoir, that should be equal to the negative of the energy, volume, and number of particles in the system. So in this case, we can set P dV as approximately 0 because it's typically very small compared to the other numbers. Now remember that when we derived the Boltzmann factor in chapter 6, we used the thermodynamic identity too, but we assumed that no particle transfer occurred and set dN to 0. In this case, we will assume that the system can exchange particles, so dN is not 0. So then we can express the difference in entropies as shown here, and the ratio of probabilities becomes this expression. So here you notice there's an exponential part, and that exponential part is called the Gibbs factor. If we want absolute probability, we need to divide it by a constant of proportionality that would make the addition of probabilities equal to 1. So that constant is called the grand partition function and is give terms. So something else we need to understand is the distribution functions. So if we consider a system consisting of only one single particle state, it will have some spatial wave function. And in this case, the system and the reservoir can occupy the same space because we're talking about bosons. So the system here is a one single particle state, and the reservoir is all other possible single particle states. So if we consider this one single particle state as an example, a particle in a box, we can let epsilon be the energy when the state is occupied by a single particle. Then if we have n particles, the total energy of that system would be n epsilon. So then the probability of the state being occupied by n particles is given by this equation, and again z is the grand partition function. And recall that the sum of probabilities is 1. So for fermions, n is only 0 or 1 because only 0 or 1 particle can occupy a same state, but for bosons, n can be any possible integer. So technically z would be an infinite sum. We can represent this sum as an infinite geometric series with x defined by this expression, the exponential part. So then the convergence of the geometric series tells us that if x is between -1 and 1, then this sum converges. So in this case, we know that Gibbs factors do not grow without limits, so mu must be smaller than epsilon, which means that the exponent part, like our x, is e to the negative number, and it's a positive number smaller than 1. So this geometric series does converge. So for bosons, it converges to this expression here. So if we want a more general description, the occupancy of the state is defined as the average number of particles in the state. So n is n with bar on top. So for bosons, remember that n is any possible integer, so this is also an infinite sum. Now recall our substitutions from before for x and the probability equation that we found before. So plugging this in our expression for occupancy, we get this expression, and then we obtain this from replacing our x and our p. And this function is the Bose-Einstein distribution. So here you can see a graph of the Bose-Einstein distribution, the Boltzmann, and the Fermi-Dirac. For Fermi-Dirac fermions, n is just 0 or 1. For the Boltzmann, there's no particle transfer, which we saw in chapter 6. And for the Bose-Einstein distribution, bosons, it's about bosons, and there is particle transfer, and n can be any positive integer. Now look at this region here. For a high enough epsilon energy of a single particle, the three curves are very similar. So how do we use this Bose-Einstein distribution? So recall the Bose-Einstein distribution. For photons and phonons, we can just set the chemical potential to 0 and assume thermal equilibrium. But for ordinary bosons like helium-4, there is a number of particles already from the beginning, and we need to determine the chemical potential, which is a function of temperature and density. Now that we have learned the mathematical tools that we need to describe Bose-Einstein condensation, let's take a look again at what it is we're trying to describe. now we can describe what we just saw. So consider the temperature as it goes to zero. All the atoms will be in the lowest energy state available because Pauli's exclusion principle does not apply. So if we consider the ground state energy for atoms confined to a box of volume L cubed, then the energy in the ground state of a single atom can be defined by the equation given. So then we can compute the average number of atoms using Bose-Einstein distribution. We're interested in the atoms in ground state, so we will call this N naught. So that is given by the Bose-Einstein distribution, and then if T is low enough, N naught is large, and because many atoms will be in the low energy state, right? And this we know this because the denominator must be small, right? The exponent is small as T is low enough, and then the exponential part can be expressed as a Taylor series, and we can consider only the first two terms. So we get this, and when T is equal to 0, the chemical potential has to be equal to the ground state energy of an atom. But when T is not 0, but it's small, mu is just a little bit less than E naught. So N naught is still large. So how small must that temperature be? So to answer this question, we need to first consider the total number of atoms, which is the sum of Bose-Einstein distribution over all states. Here we can convert it to an integral over the individual energies. So G epsilon is the density of states, which is defined as the number of single particle states over unit energy. And it is given by the following equation, where V is the volume, h bar is Planck's constant divided by 2 pi, epsilon the energy of a single atom. So this integral unfortunately does not have an analytical solution, and we must guess the value of mu. Start with a guess of mu equals 0. That gives us this expression, but this expression implies that the number of atoms depends on temperature, which is not true. The answer is only valid for one value of temperature, which is the condensation temperature. So what happens when the temperature is greater than the condensation temperature? Well, mu must be less than 0. It should be negative so that N naught is a smaller number, because essentially all the atoms are in excited states. So remember, N naught is the number of atoms in the ground state. When the temperature is lower than the condensation temperature, mu is close to 0, and the number of excited atoms, not including ground state, is approximately the same as for the condensation temperature. But in this case, the expression, the right-hand side looks the same, but N is not N naught, is N excited. So we know the expression for N valid at Tc, so we can write then the number of excited atoms as follows. And remember that the total number of atoms is the sum of ground state atoms plus excited state atoms. So we can write the number of ground state atoms as the total atoms minus the excited atoms, and we get this expression. Now if we graph this, the number of atoms in ground state versus temperature, and the number of excited atoms versus temperature, we can see that there is this sudden increase as we go lower in temperature, as we go below the condensation temperature. There is an increase in the atoms in the ground state. So that is the Bose-Einstein condensation. And we call those atoms that appear here the condensate. We can also look at a graph of temperature dependence on the chemical potential. We can see here Tc looks 0, but in reality it's not 0, but it's very small. Now let's talk about the evidence for Bose-Einstein condensation. So Einstein's predictions were not verified experimentally until 1995. The first case was a gas achieved with weakly interacting atoms of rubidium-87. This experiment consisted of 10 to the 4 atoms confined in a volume of about 10 to the negative 15 meters cubed. When the temperature lowered to around 10 to the negative 7 Kelvin, most of the atoms were condensed to ground state. This was surprising because the individual atoms would normally be in the ground state at temperature 100 times lower than that. Here we can see the pictures of that experiment. So in the first picture here, above the condensation temperature, the velocity distribution is broad and isotropic, and it's described as Maxwell-Boltzmann distribution. Below the condensation temperature, which is this middle picture, most atoms fall into a small region in velocity space, and the atoms we're seeing here are the atoms that form the condensate. And at the temperature of approximately absolute zero, essentially all the atoms are in the ground state wave function. So why does Bose-Einstein condensation happen? Well, it happens because of the combinatorics of counting ways of arranging identical particles. As we can see in these graphs, the number of distinct ways of arranging identical particles among excited states is very small compared to those of particles that are distinguishable. You can arrange them in many more different ways in excited states. So in the case of identical particles, like bosons, because they don't follow Pauli's exclusion principle, ground state becomes much more favorable for them. So yes, that was all my presentation, and I hope you enjoyed it. Thank you.